Today, in this video, we will see beam design. Our beam design question is wall 230 mm thick and height 4 meter above the beam. Simply supported at ends. Effective span is 4.6 meter. Density of brick is 20 kilonewton per meter cube. Use M25 grade of concrete and Fe 500 steel. Given wall 230 mm thick, height 4 meter, above beam, simply supportive at ends, effective span 4.6 meter. This term effective span means this is beam, this is column. Sorry for my drawing. Span between center to center of column. Wait a minute. This is beam. This is column. Distance between center of column to center of column is effective span. And what is clear span? Clear span is inner distance of column. This is clear span. So in numerical, they have given us effective span. For design, we take effective span. Density of brick 20 kilonewton per meter cube, M25 grade of concrete, Fe 500 steel, and nominal cover M20. Nominal cover is section of beam. This is section of beam. This is stirrups. Nominal cover is this distance. Outermost, from outermost distance to the stirrups distance. This is nominal cover. And another term is effective cover. Effective cover is nominal cover plus half diameter of stirrups. Effective cover is nominal cover. Effective cover is nominal cover plus half. Here is the main bar. Diameter of stirrups plus half diameter of main bar. They have given us nominal cover 20 mm. So step by step we see design. Step 1. Assume span by D ratio between 10 to 15. This is thumb rule. Assume span by D ratio between, sorry for my handwriting, 10 to 15. So take span by D equal to 15. Between 10 to 15, any value you can take. So I take 15. My span is, in numerical, they have given 4.6 meter effective span. So in mm, I write 4600 upon this 15 I take in denominator 15 equal to D. So 4600 divided by 15 value comes 307 mm. D equal to 307 mm. This D is effective depth. Effective depth is, this is the section of beam. This is stirrups. Effective depth is, this is anchor bars, this main bars. Effective depth is between top distance to the this distance. Small d. Half of to the half of main bar distance. We see next slides this distance also. So assume total depth. Therefore, assume total depth capital D equal to 400 mm. Total depth capital D. Next step 2. Calculate load on beam per meter. Wall load, first wall load. They have given wall height is 4 meter and wall thickness is 230 mm. So 230 mm I write in meter, 0.23 meter into 4 meter, that means 0.23 meter and height is 4 meter into 20 is the density of wall, 20 kilonewton per meter cube. Value comes 18.4 kilonewton per meter. This is in meter, 4 in meter and 20 kilonewton per meter cube. Meter square cancel, kilonewton per meter value comes. 2. Self weight of beam. We assume 400 depth of beam, and width of beam is wall width of. So we take beam similar width as a wall and depth 400. So 0.23 multiplied by 0.4 multiplied by 25 is the RCC density. Value comes 2.3 kilonewton per meter. So this wall load and this self weight of beam acting on beam, this 18.4 kilonewton per meter wall load uniformly distributed acting on beam. So total working load this 18.4 kilonewton per meter plus 2.3 kilonewton per meter $20.7 kilonewton per meter total working load on this beam. Factor load, for safety side purpose we take factor load. Limit state method design, we take factor load equal to 20.7 into 1.5. We get value 31.05 kilonewton per meter. Next, step 3. Maximum bending moment. So beam is simply supported. In example, they have given us simply supported ends. So the simply supported beam bending moment formula is WL square by 8. Total factor load acting on beam 31.05. So W is 31.05 multiply by effective span 4.6 square by 8. We get value 82.12 kilonewton meter. We get factor moment 82.12 kilonewton meter. Maximum, next calculate maximum shear force. WL by 2. Factor W is 31.05 multiplied by effective span 4.6 divided by 2 equal to 71.42 kilonewton. This is shear 71.42 kilonewton shear and 82.12 kilonewton meter maximum bending moment we get. Next, step 4. Check for effective depth. Effective depth check formula is mu limit equal to 0.138 FCK BD square. So for effective depth, D square equal to mu limit divided by 0.138 FCK B. Mu divided by 0.28 FCK B. D is equal to under root of mu limit, simple mathematics, 0.138 FCK B. Therefore, D equal to, our mu limit is this moment 82.12 kilonewton meter. I convert it into Newton mm. 82.12 kilonewton meter. 82.12 kilonewton meter is converted into Newton mm. So 10 raised to 6 multiply divided by 0.138. FCK is 25. In numerator they have given us M25 grade of concrete. This is FCK 25 and B is 230 width of beam. D equal to, we get value 321.70 mm. Therefore, provide total depth as capital D is equal to 400 mm. Provide total depth capital D is equal to 400 mm. Next step. So, assuming 20 mm diameter bars and 8 mm stirrups, for calculating effective cover, assume step 6, step 5. Assume 20 mm diameter bars and 8 mm stirrups. Effective cover is, in numerator, in numerical, they have given us nominal cover. So we calculate effective cover. Effective cover is nothing but the nominal cover plus stirrups diameter plus main bar diameter divided by 2. So in section, this is beam, this is stirrups, these are anchor bars, these are main bars. Nominal cover is this distance is nominal cover. Nominal cover they have given us in numerical 20 mm. So we calculate effective cover. This is stirrups. Stirrups diameter is 8 mm and main bar diameter 20 mm. We assume. So nominal cover 20 plus stirrup diameter 8 plus main bar diameter 20 divided by 2 up to middle of this main bar. This much distance is effective cover distance. So 20 plus 8 plus 10, 38 mm, we get effective cover. And from top to this distance, middle of main bar distance, small d, is effective depth. So what is effective depth? Our beam total depth is 400 mm. So 400 mm minus 38 mm effective cover minus, so the effective depth small d value comes 362 mm. This effective depth value comes. For that depth we design beam 362 mm. Next, step 6, main steel calculation. AST formula 0.5 FCK divided by Fy multiplied by 1 minus under root of 1 minus 4.6 mu movement divided by FCK into B into D square multiplied by B into D. That D is the effective depth, B is the width of beam, FCK is the concrete M25 FCK, mu movement Fy 500 steel. So 0.5 into FCK 25 in numeric Fy 500 1 minus 4.6 mu. Our mu is this 82.12 kilonewton meter. Convert it into Newton mm. 82.12 kilonewton meter conversion Newton mm multiply 10 raised to 6. FCK 25. B is 230. And D is effective depth. We calculate our B. D is 362 mm. 362 mm multiply by B into D 230 multiply by 362. Calculate all this in calci. We get value 608 mm square. This is required area of steel in beam. 608 mm square required area of steel. So number of bars provided. We assume initially 20 mm bar diameter, 20 mm bar diameter and 8 mm stirrups. So calculate number of bars. Equal to 608 upon area of 20 mm bar diameter, pi by 4 into 20 square. So value comes two numbers bar 20 mm diameter. Therefore AST provided equal to 2 into pi by 4 into 20 square equal to 628.31 mm square. Provided AST is greater than required AST. Okay. AST provided greater than AST required. AST provided is 628.31 mm square and AST required is 608 mm square. Next step is check for width. Step 7. Check for width. Formula 2 into clear cover plus stirrups diameter plus 3 into main bar diameter plus 2 into spacing between bars. Two into clear cover. One more term is there. Nominal cover and clear cover is same. So clear cover is 20 plus stirrups diameter 8 plus 3 into main bar diameter 20 plus 2 into spacing between bars. It's 5 mm more than main bar diameter. So our main bar diameter is 20, 20 plus 5, 25 spacing between bars. After calculation of this, 2 into 20 plus 8 plus 3 into 20 plus 2 into 25, 166 mm value comes. This is required width of beam. So we provided 230 mm width of beam is greater than 166 mm required width. So the provided width is okay. Next calculation is design for shear. Step number 8. Percentage of steel provided equal to AST provided upon B into D into 100. Our AST provided is 628.31 divided by B into D, where beam width is 230 into effective depth is 362 into 100. Value comes 0.75%. Percentage of steel provided 0.75%. So next step 9. Shear stress resisted by concrete. shear stress resisted by concrete, tau c. This tau c value we get from IS 456 table 19. I show you IS 456. Wait a minute. Shear stress resisted by concrete, tau c value we get from table 19 IS 456. So our percentage of steel provided value comes 0.75 mm. Sorry, 0.75 percentage. This 0.75 percentage and our concrete grade is M25. M25 0.75. So our tau c comes 0.57. 0.57. 0.57 tau c we get from IS 456. Therefore, shear force resisted by concrete is tau c 0.57 multiplied by width of beam 230 multiplied by effective depth of beam 362 divided by 1000. Kilonewton value we get, that's why we divided 1000. So value comes 47.46 kilonewton. That much shear force, 47.46 kilonewton, resisted only by concrete. And our calculated shear force is this, 71.42. This much shear force comes on beam and concrete only takes this much shear force, 47.46. Concrete takes less shear force than required shear force. That's why we provided stirrups. Therefore, provided stirrups. Using 8 mm diameter 2-leg stirrups. This 2-leg stirrups means this is stirrups, this one leg and this 2-leg, this 2-leg stirrups. Area of stirrups is 2 into pi by 4 into 8 square. 2 into area of 8 mm diameter bar. We get value 100.53 mm square. Now calculate spacing. Spacing for stirrups. So how we calculate spacing for stirrups? SV equal to, from IS 456 clause number 40.4 page number 73. IS 456 clause number 40.4 page number 6, page number 73. I show you IS code, page number 73. For vertical stirrups, this formula. From this formula, we calculate SV. SV is the spacing of stirrups or bent up bars along the length of the member So SV formula we take from IS 456. Formula is 0.87 FY ASV D effective date on VUS equal to 0.87. FY is still 500 multiply by ASV, calculated ASV 100.53 multiply by D effective date 362 divided by VUS. VUS is this required 71.42 shear minus shear force resisted by concrete 47.46. That means additionally, I show you, shear force required 71.72 minus shear force resisted by concrete 47.46. 71.42 minus 71.42 minus 47.46, 23.96. This much additional shear stress required. This much additional shear stress resistance required. So, and this is in kilonewton. Multiply 10 raised to 3, convert it into Newton, and calculation of this is 660.70 mm. This spacing comes, but the spacing is very big, and in IS code there are provisions. They tell us, page number 47, IS 456. Spacing of shear reinforcement measure along the axis of the member shall not exceed 0.75 D for vertical stirrups and D for inclined stirrups. 0.75 D and D for inclined stirrups at 45 degree, where D is the effective depth of the section. In no case shall be spacing exceed 300 mm. So spacing should not be greater than first 0.75 into effective depth and second 300 mm. 0.75 into our effective depth is 362 mm. 0.75 into 362, value comes 270 mm. 272 mm. Therefore, provide 8 mm diameter 2-leg stirrups with 250 mm center to center. Next is check for deflection. Next is check for deflection. Step number 10. check for deflection. L by D equal to L is our effective depth, convert it 4.6 meter conversion in mm, 4600 mm divided by, sorry, L is effective length 4.6 meter, convert it into mm, 4600 mm, effective depth is 362, value comes 12.70. This is in mm, effective depth is also in mm, value comes 12.70. In IS code, clause number 23.2.1, basic value of span to effective depth ratios for span up to 10 meter for simply supported is 20. Our value comes 12.70 mm is less than 20. Okay. IS 456 clause number 23.2.1. Next is effective. Next is development length. Step 11. ELD. This development length formula we get from IS 456 page number 42. Development length of bar, the development length LD is given by LD is equal to 5 into sigma s into upon 5 into tau BD. Phi is the nominal diameter of bar. Sigma s is stress in the bar at the section considered at design load. Tau BD is design bond stress in 26.2.1.1. Design bond stress, our grade of concrete is M25. So design bond stress is 1.4. So take this formula, LD is equal to 5 sigma s upon 4 into tau BD. Phi is our diameter of main bar 20 into sigma s is our steel grade is 500 multiplied by 0.87. Stress in bar at the section considered at design load upon 4 into tau BD. Our tau BD is design bond stress given in 26.2.1. Design bond stress tau BD. Our grade of concrete is M25. Take value 1.4. 1.4. Calculate this 20 into 500 into 0.87 divided by 4 into 1.4. Our value comes 1554 mm. This much development length needed for detailing. So next. These are main bars. These are anchor bars. And these are stirrups. Here, column. This much is the effective length, 4.6 meter. So our design is 8 mm diameter, 2 leg stirrups, 250 mm center to center. Our main bar design is 20 mm bars, provided bars. Two bars we provided. Provided AST is 628.31, 2 bars of 20 mm diameter. Main steel, 2 bars, 20 mm diameter, and anchor bars, 2 number, 10 diameter. Development length we calculated 1554 mm from here to here. This much distance, 1554 mm. Section XX of this beam is 2 leg stirrups, two anchor bars, this stirrup, 8 mm, 2 leg, and these two number of bars, 20 diameter, and these two number of bars, 10 diameter. So our design is complete. Thank you very much.